So a polynomial expression is an algebraic expression that combines numbers and variables with arithmetic operators. Okay, now that's just a fancy way of saying they're expressions that have variables, have numbers, things we've been working with so far. That little light is bothering me. So how is this different from an algebraic expression? Well, the difference here is that a polynomial is going to be specific with respect to the exponents that we have on the variables. So variable terms can only have exponents which are, let's say, whole numbers. Okay. So let me give you an example of a polynomial. Let's go example A. This is our polynomial. 5. Just the number 5. Now, this number is just a number. The arithmetic operators that we see here are none. It's just the number 5. This is kind of like the simplest kind of polynomial. We call this a constant polynomial expression. And the reason why we can think of this as having a variable is because last time we said that, if you recall, that the 0 power rule says x to the 0 power is equal to 1. Okay. So this expression right here that just has a single number, even though we typically just think of it as the number 5, we could, if we wanted to get really zany and creative with it, we could say, okay, what if we multiplied 5? So what if we took 5 and we multiplied it by x to the 0 power? Well, then you could just call that 5x to the 0 power. You don't have to put the little dot for multiplication. And then this sort of looks like a variable term. But based on our 0 power rule, we know that that is equivalent to 5 times 1, since x to the 0 power is just 1. And that's just 5. So all of these expressions that I just showed you here are equivalent expressions to just the number 5. So in that sense, a number by itself could be expressed with a variable, any variable, raised to the 0 power, since that x to the 0 power or y to the 0 power, whatever the variable is, this guy to the 0 power is always going to be just multiplying by 1. Okay. So you can think of all the numbers on the number line as being the simplest kinds of polynomials. Okay. We just weren't calling them polynomials before. And we typically won't be calling them polynomials. We'll just call them constants. But here, let me give you another polynomial. So example B would be something like 3x plus 7. Okay. So in this polynomial, we have 2 terms. Okay, so this is going to be sort of a vocabulary word that I'll use, and I've used it before, but now I want to be really specific and explicit with this word terms. Terms the way you can count the number of terms in an expression is that terms are separated by the addition or subtraction symbol. So we have two terms here. We have 3x, and it's separated by the addition sign here, and 7. So this is a two-term polynomial. We have a variable term. We have a constant term. And for two-term polynomials, we have a special name for them. We call them binomials. Okay, now the prefix here bi tells you that there are two terms in that expression. Okay, so at this point, what I like to do is break down the etymology here. Why do we call them polynomials? And we'll jump back into some examples here to look at some crazier polynomials. Okay, so what does polynomial mean in a linguistic sense, right? Well, poly is the Greek, comes from the Greek word which means many. And nomial comes from Latin. And I always relate it to Spanish. Since we're in Texas, we probably know enough Spanish to get us by. But this just means names. In the same way that nombres, right, means names in Spanish. So in this linguistic sense, we can understand that a polynomial literally means an expression that has many names or many terms that you're just adding and subtracting together. Okay, so let's look at example C. You might have an expression that looks something like this. And so if you needed to count how many terms are in this expression, how many terms are here?
3.
Yeah, absolutely, right? There's a term right here, a term right here, and a term right there. So we have a 3-term polynomial. And we call these specifically trinomials, which means 3 names or 3 terms. So again, the fancy terminology polynomial is sometimes intimidating, but really if you just break it down, it just means that we have these algebraic expressions, things that we've been dealing with that have multiple terms. Okay. Well, there are some algebraic expressions that we'll run into later in the semester, but we'll have to be able to say whether or not this is a polynomial. So is this a polynomial? So let's do this. 9p to the 5th power minus 3. Is this a polynomial? Like based on the definition that hopefully you guys had enough time to write down, is that a polynomial?
Yes.
Because it's just a simple algebraic expression. It combines numbers and variable terms with the addition and subtraction. So we have two terms here, and we have a power that's a whole number. Okay, so yeah. Okay, let's try 10x to the third plus 8x squared minus 37 plus 19x to the negative 7. Okay, what about this one?
Yes.
Why yes?
Because has 1, 2, 3, 4, 5 terms. No, 4.
1, 2, 3,
4 terms.
4 terms. Yeah, there are 4 terms in the
Divided
expression.
for plus, for addition and subtraction symbol.
Right. There's addition and subtraction here. But what about the exponents?
But the other one has exponent too.
Yeah, so all of them have exponents. You can think of this as being x to the 0 power, right? It could be 37x to the 0 power. That would be the same thing. But I threw this term in here, x to the negative 7th. And if I just flip back to the definition that I gave you a little while ago, the variable terms can only have exponents which are whole numbers. So what I mean here is that we can't have any negative exponents in any of the terms or fractional exponents, which we haven't seen any fractional exponents yet, but they're coming in the third unit in the third module. So we'll cross that bridge when we get there. But what you want to look out for when you're trying to assess whether an expression is a polynomial is, do I have any negative exponents? Do I have any fractional exponents? And because I threw this negative 7 exponent on that final term, well, that sort of throws a wrench in this system, right? Where this can't be a polynomial because of this one, because of this term. So we're going to have to say no here because of the negative exponent. Does that make sense? Okay, and I'm thinking that the negative exponents will be easy to identify when you can see them clearly like this, but let me give you another expression and ask you the same question, right? Is this expression a polynomial? So what if I did 9x squared minus 4x plus 6 over x squared? What do you guys think about this one?
No, because you have a fraction?
Well, that's a good assessment. So I'm going to say yes. But let me give you another example real quick, and then we'll go back to this one. What about 1/2 x to the third power plus 1/4 x squared minus 1/7? What do you guys think about this one? Well, now it's maybe not so clear, right? These are sort of different from each other. There's fractions in both of them. And now it sort of feels like I'm giving you a trick question, right? Well, for this expression here, we have something at the bottom of this denominator for this fraction. And that's not the same as these terms in this expression, because this is just 1/2 times a variable term. And that's perfectly okay. You can have fractions, you just can't have fractional exponents. Okay. So fractions multiplied by a variable term is okay. So since we have a number multiplied by a variable, a number multiplied by a variable, those variables both have exponents that are whole numbers, and then these terms are separated by addition and subtraction, this one is a polynomial. But this one is not. Okay, so number 3 is not. I just realized that I went from numbering in letters to numbers. In any case, this is not a polynomial because whenever you have a variable term in the bottom of the denominator, I don't know if you guys remember this, at the end of class last time, so if you recall, we had this negative exponent or negative power rule, which said that if we had a to the negative n power, that is the same thing as 1 over a. Right? We flipped it to the reciprocal. It went to the bottom of the fraction. So what that means for this expression is that we could rewrite it leaving the first two terms alone because there's nothing there that we can sort of rewrite. We could leave that as 9x squared minus 4x. But this term here, because you have x to the second power in the bottom of the fraction, you could rewrite it as plus 6 times x to the negative 2 power. So this guy, if we wanted to bring it up to the top of the fraction, it's actually a negative power based on this negative exponent rule. So if you guys wanted to see that in action, right? If I had x to the negative 2, that's the same thing as 1 over x squared. So since we had this x squared in the bottom, it really goes both ways. We have to think about it both as 6 over x squared and at the same time 6 times x to the negative second power. So because we have that negative exponent, this is not a polynomial. Because of this term. Okay, so the easy way that you're going to sort of differentiate, right, is that variable terms cannot be at the bottom of a fraction, because that's equivalent or equal to a negative exponent. Okay, so that's the full rationale, but basically what you're going to say to yourself is if there's a variable term at the bottom of a fraction, then that's not a polynomial. Okay. You can have fractions though, right? You can have something like this where there are fraction coefficients that go with the variable, but that variable term cannot be at the bottom of the fraction. So let me give you another example. Let's switch back to oh no, that's fine. Numbers. Let's switch. Let's look at 1/2 x to the 7th minus 8. Is this a polynomial?
Yes.
Yeah. Yeah, no trick questions there. just trying to get you guys used to identifying why this one is a polynomial. And the reason why it's a polynomial is because my exponent is a whole number. But if I wrote something that's really similar, let's do 1 over 2x to the 7th minus 8. This is a different expression. It's not the same, even though I use the same numbers. So is this one a polynomial?
No.
No. Yeah, I'm not trying to make it difficult for you guys. Because I can rewrite this as 1/2 and then take this variable term and say to myself, well, okay, when I have 1 over x squared, that's the same thing as x to the negative 2nd power. Then this expression here is really 1/2 times x to the negative 2nd power. I'm sorry, negative 7th power. Let me change these to 7s. There we go. Minus 8. So because this guy is at the bottom of the fraction, and you'll see it clearly that it's at the bottom of the fraction bar, as opposed to next to the fraction, that's what signals to you that this guy is not a polynomial, because it's really a negative exponent. Okay. Well, there's definitely some problems like this in the homework that I'm going to post here in a little bit that ask you to identify whether something is a polynomial, but they also ask you some other terminology about polynomials. So I need to introduce this concept of degree. So the degree of a polynomial is either the highest exponent on a variable term, or the highest sum of the exponents on a term with multiple variable factors. Okay, those probably sound a lot like the same thing, but they're actually not. So let me give you an example of these. So let's go with some examples. So if I asked you what is the degree of this expression, let's do 10x squared plus 7x minus 13. And again, the degree is either the highest exponent on a variable term. You might note to yourself that this expression only has one kind of variable. So we only have a single variable here. And that variable is x. So the degree for this polynomial comes from the first term here because it has the highest exponent, which is 2. So we would say that this is a polynomial expression of degree 2. Okay, and the term that has the highest degree or the highest exponent, we call the leading term. And it doesn't matter in what order these are placed, you're always going to look at what term has the highest exponent. That's going to be the leading term. And then that's how you're going to determine what the degree is. Okay. So we could have something like this: x plus 3x to the third minus 45x to the seventh plus 10x to the second. And now if I asked you, what is the leading term of this expression, would you guys be able to figure that out?
Negative 45
45x.
to the seventh power.
Yeah, it's this term here, and I'm going to go ahead and box in the term. So the leading term is negative 45x to the seventh power. That whole thing is the leading term. Okay. Sometimes you'll need to know what they'll ask you, what is the leading coefficient? And that's just the number that's being multiplied by the leading term. So the number that's in front of the variable here is negative 45. But if I ask you what the degree of this polynomial is, the degree is just given by the exponent on the leading term. So that's just a 7. So this is a 7th degree polynomial. So we're just sort of classifying these things because there's different types of polynomials that we deal with in algebra. And so just as an aside, you guys have seen already expressions that we were calling linear algebraic expressions, things like x, let me call this 3x plus 2. Well, it turns out that this linear expression is what degree polynomial?
One.
Yeah. So for linear expressions or linear equations, the highest power on the variable here, well, we just have x, but because we don't see a variable, I'm sorry, an exponent, it's an understood 1, right? That's why we went over the power of 1 rule at the very beginning of class last week. So linear expressions are polynomials of degree 1. So all this time when we were solving linear equations, we were really, at the same time, not knowing it, solving these linear polynomial expressions of degree 1. That's another fancier way you could describe that. Okay. Okay, so the tricky thing is this part, the highest sum of the exponents on a term with multiple variable factors. Okay, so you might see some in your homework, although we won't see a lot of them throughout the rest of the semester. I'm pretty sure that this is the only homework assignment where you will have algebraic or polynomial terms that have multiple variables in them. But I want you to be able to get over that hump, get over those problems successfully. So if I gave you a problem that had negative 3x to the 5th, y to the 8th, plus 10x to the 6th, y, let's go with minus 7x to the 9, y to the 3. Okay, there are 3 terms in this polynomial, but there's 2 different variables on each of the terms. Okay, so can anybody here determine, okay, which one of these is the leading term and what is the degree of the polynomial?
Would the leading term be 10x to the 6th power y?
Why did you choose that one?
Because 10 is bigger than all the other numbers.
Mm-hmm. Now that's a good argument, right? That 10 is the biggest number, right? But I'm looking for the leading term, and the leading term is determined by the largest exponent.
Negative 7x 9 to the y.
Yeah. So the degree of the polynomial is either the highest exponent on the variable or the highest sum of the exponents on a term with multiple variable factors. So each of these terms has multiple variable factors. So we have x and y that are being multiplied by each other, right? So what we have to do in our heads is say, okay, for this term, if I add the exponents up, 5 and 8, I get 13. For this next term, 6 and this is a 1, if I add those up, I get 7. And then here, 9 and 3 make a term that is what? The 12th? My brain is not, I needed way more coffee than I had this morning. Yes, it is 12.
So then it'd be -3.
Yeah, so we would say that this is the leading term. The leading term is -3x to the 5th, y to the 8th. The leading coefficient is just that -3 in the front. And then the degree of this polynomial is 13. Does that make sense? Or does anybody have questions? So I would say that if you're able to identify, by looking at a variable, a polynomial expression, able to identify what the leading term is, the leading coefficient, and the degree, that you should be pretty good to handle those particular problems in the homework. Okay. So I think that we are now ready to do some operations with polynomials. Okay. And that sounds a lot more excruciating than it's actually going to be, especially right up front. But what you have to realize is that math is more than just numbers. This is going to sound really strange, but once you get to a higher level of mathematics, there cease to be any numbers, and you're just working with things called objects. And if some of you, or if any of you are familiar with any kind of programming language, I don't know if anybody has dabbled in HTML or Java or Python. There are certain kinds of programming languages for writing software that are called object-oriented languages. Now, this is just me trying to connect this idea of objects to something that you would understand. So an object is just a thing. It is anything. The simplest kinds of objects that mathematicians work with are numbers. And we call them real numbers. That's pretty much all that we're going to see here. But then there's another class of objects that are called complex numbers that we will see a little bit later on in a few more sections. And the complex numbers have imaginary numbers sort of thrown in there. But there's all sorts of objects. There are things called fields that mathematicians work with. Again, you wouldn't ever really use numbers to describe the major features of these things. Matrices are a kind of object that we've worked with already. And now we're just throwing one more type of object at you, which is a polynomial. Okay. this is just to give you an overview of like all the kinds of things that mathematicians work with. If you hear people talk about different fields or groups or algebras, you might not actually ever hear anybody talk about those things because that's like a really esoteric form of high level math. But I just wanted to, introduce you to this idea that mathematicians study objects, their processes, and their properties more than just adding, subtracting, multiplying, and dividing numbers. But anyway, the operations that we're doing with these polynomial objects are very similar. They're analogous to working with numbers. Okay, so we'll start off with adding and subtracting polynomials. Okay. So I'm just going to write down a problem and then see if you guys know how to add them. And I sort of suspect that you do because we've already been doing it. 2y to the fourth minus 3y to the second power plus y. This polynomial is being added to another polynomial, which is 4y to the fourth power plus 7y to the second power plus 6y. Yeah, just 6y. So we have 1, 2, 3 terms here. So if you wanted to, you could sort of say, okay, this is a trinomial. A trinomial being added to another 1, 2, 3, another trinomial. But I want you guys to just jump in and give it a shot. What do you think you get when you add these two polynomials together? How could we simplify the expression?
Would you add the like terms?
Yeah, that's all you're doing. When you're adding polynomials, you're just combining like terms. So what I tell students so that they don't get confused here is that when you're adding polynomials, just drop the parentheses. They're not necessary. You could read this as 2y to the fourth minus 3y to the second plus y plus 4y to the fourth plus 7y to the second plus 6y, right? It's a lot of writing. Polynomials are long, but that's about the only thing that makes them complicated, just that there's a lot of terms. To simplify them or to just add them, we're just going to combine like terms like we've always been doing. Well, always in this class. So we have this guy, those are the same. That guy is the same as that one. And then finally we have this guy and this guy that are the same. So when you guys simplify that, what should I be writing down?
6y to the fourth power
6y
plus
to the fourth
plus 4y to the second power
plus 4y to the second
plus 7.
plus 7y. Yeah, that's the answer. You've just added, I want to say you just added your first polynomial, but you've just thought about them as polynomials and added them that way for the first time, right? But it's
And
just,
the exponents stay the same?
yeah. I mean, why should they change? You think about it like you did with combining like terms. You had y to the fourth power. That's like apples. So if I have 2 apples and 4 apples, then I should have 6 apples. The name stays the same. If I have -3 oranges and 7 oranges, then really I only have 4 oranges. 1 banana and 6 bananas, I have 7 bananas. Okay, so when you're adding or subtracting polynomials, the exponents don't change. The exponents or the names don't change. Now, that was a good question and good comment because students often make the mistake of trying to change the polynomial. But like, I want you to understand what you're doing and why you're doing it. We'll see in a second when we start multiplying polynomials that the exponents will change, but there's a reason for it. Okay, let's do another example.
A question really quick. So you cannot, because it's y is y, so you cannot add 4, 2, and 1, the exponents, even if it's y.
Right,
So you cannot do that.
right. Let me think about this. Think about it this way. Like, let me give you a sort of simpler example. 2. Let's say we had 3x squared minus 5x plus 10x squared minus 13x. Okay. Go ahead and do this one like we did the last one, and I'll try to sort of explain why we can't add them when they have
The
different.
same way, it will be
Mhm.
13x 2.
Yeah.
And then, how does it? 18 minus 18x.
Yeah, perfect. Okay. That is exactly how you would go about adding these two polynomials. I didn't really throw, if I had thrown parentheses around it, it would have made more sense. There we go. We're adding two polynomials, but we're just combining their like terms, right? We had this guy combined with this guy, and then this guy combined with this guy. All right, but the reason why we can't add these two is because they're two different kinds of quantities. Imagine that, you know, you wanted to measure the square footage of your house, and you measured 13 square feet. That's a different kind of unit from linear units when you just measure like the length of the wall. A square foot is literally 1 foot in this direction, 1 foot in that direction. So this is a square foot. I don't know if this analogy is making any sense. As opposed to, I'm going to leave this as 18 feet, where that would just be a linear measurement from 0 to 18 feet, right? So these objects are different from each other, which is why you can't add a squared term to a linear term. So if that's helpful, like it wouldn't make any sense to add my height to the square footage of my house, because like my height is just a linear measurement. It's a linear unit. It's a linear variable. And this is just a different kind of variable. But that's why I say like the easier way to think of it, or like the really sort of childlike way to think about it, is just apples, bananas, and oranges, just different fruits. They're different things when they have a different exponent on them. So since they're not like terms, you can't combine them. You just have to remember, oh, just because they have an x doesn't mean that they're like terms. They have to have the same variable and the same exponent. Any questions about that little discussion?
No. Okay, thank you.
Cool. Yeah. Okay, let me give you another example. Let's see if you guys can do this. I'm going to have -3m to the third power minus 8m to the second power plus 4. Got a trinomial here, minus m to the third power plus 7m to the second power minus 3. So we have here, just to break down what we're looking at, we have 1, 2, 3 terms. So this is a trinomial. Minus 1, 2, 3 there. So that's a trinomial. So really it's trinomial subtraction. But we've seen this before. So if I asked you to simplify this expression, you would be doing the same thing as subtracting polynomials. So what should I do for the first step in simplifying this expression?
Was take out the parentheses, like minus 3m3
Yeah.
minus m2 plus 4. And the minus is multiplying the parentheses. So it's
Yes.
like m3
Exactly.
and then 7m2 plus 3.
Yeah, okay, exactly. That's perfectly correct. So for each of the terms that are being subtracted, we're really subtracting this, and this. So it's the same thing as thinking about distributing a -1 here, here, and here. So what I would say to solve these subtraction problems, whatever's behind the subtraction sign, distribute that like a -1 first, and then drop the parentheses. So we'll have -m⁻³ minus 7m² plus 3. And then we can go ahead and drop the parentheses entirely here and just bring all of the terms in this polynomial down, -3m³ minus 8m² plus 4, and just combine like terms after that. So we have, again, I like to go and scoop up the like terms by using a different color or a different shape. So I might do a double underline for my m⁻³ power. Might do a circle for these guys, m⁻² power, and then my constant terms, I might use a square, just so visually they're distinct. So what should I get when I simplify and combine like terms now?
Minus 4m³ power minus 15m² power plus 7.
Minus 4m⁻³, boom, boom. That would be 15 minus 15m² and plus 7. Yeah, that's it. Don't have to overthink that. It's just distribute the negative sign, combine like terms. This feels pretty familiar to what we've been doing so far, right? Nothing new or out of the ordinary here. Maybe a little bit of refreshing stuff. In case you forgot, like that was a good discussion on why we combine like terms and why we can't add these two terms together. But aside from that, it's sort of the same old as far as what we've seen before. Okay. So now I'm going to give you a set of problems that I want you guys to take about 10 minutes to work on. I'm going to throw you guys into breakout rooms so that you can work with each other. And then we'll talk about multiplying polynomials. So let's see. Let me write these down. 17x³ minus 10x² plus x plus third plus 10x² minus 5x b. I'm going to put -6m⁴ minus 11m² plus 21 minus m⁴ minus 6m² plus 35. And then 6z² minus 5z plus 3 minus 4 3z to the second minus 2z plus 9. Okay. Take a moment to write these down. And once you do, let's go ahead and okay. So how did you guys feel about these practice problems? I think I see some head nodding. So I'm assuming that means that this is pretty straightforward, right? Not anything out of the ordinary. It's just that we're calling it a fancy, I'm calling them fancy things, but you're probably in your head just saying combine like terms, distribute or multiply, and then combine like terms, right? So like even without using the fancy terminology of adding two trinomials here, multiplying a trinomial by a number, multiplying a different trinomial by a different number, and then subtracting. That's what we're doing. Okay, so what did you guys get for this first practice problem when you simplified it?
5m to the fourth plus 17m squared minus 56.
Oh, hold on, the first one had the x's in it.
Oh, shit. 8x to the third minus 4x.
8x to the third, that looks good to me. Let's go ahead and circle those guys, box in these guys. Oh, those are opposites, so they should cancel out because we get 0. And then this and this are -4. Is that what you said?
Yeah, minus 4x.
Minus 4x. Yeah, that's perfect. Anybody else have something different, or did you realize what your mistake is or have trouble with that one? You need clarification is basically what I'm asking. Okay. Yeah, I think that adding is probably the simplest thing you could do with polynomials. This subtraction problem, I threw a little bit of a complicating factor here by subtract or multiplying by a negative here in the front. But what did you guys get when you simplified this one?
The final answer or the process?
You could walk me through the process.
We got 6m4
Yeah, this should have been 6m to the fourth
plus 11m squared
11m squared
minus 21
is 21
minus 4m to the fourth power
minus m to the fourth
plus 6m to the second power minus 35.
Yeah. And then when you guys combine like terms,
We got 5m to the 4 plus 17m to the second
17m to the second
minus 56.
I'm going to take your word for that one. No, that looks right. Yeah, that looks good to me. Okay. Anybody else want to take a crack at this last one? Or do you want to walk me through the process here?
Okay, it's 6 multiplied by c. Well, it's 6c.
Yeah, we can just say we'll just distribute the 6.
Distributed.
So you should have what?
6c2
Okay.
minus 30z
Yeah.
plus, hold on, I think I make a mistake right there.
18.
Yeah, 18.
Yeah. 18.
Minus 12z plus 8z minus 9. No, yes. See, I make a mistake again.
Yeah. So that's a common mistake. I'm glad that you're making it. Thank you. Because a lot of students will make that mistake when they're, on autopilot. So just make sure that you take this number and that you're distributing it to every term. And that's exactly why I draw those arrows every time, so that I remember this gets multiplied by right here, here, and here. So don't forget that last term.
And then it will be minus 6z.
Yeah, exactly. Minus 6z.
To
the second power, good.
the second power. Minus 22z.
Minus 22z.
Minus 30, no, sorry, because I have my other, other version.
Yeah, so this guy and this guy should give us -8.
Okay.
Yeah, and again, if you needed that visual, distinction, we could take our exponent of 2 there, take our single variable, and then give it just different markings, right? Just so that we can visually distinguish the like terms. Okay, so here's what I want to do. Before we get into multiplying polynomials, I want to take a 10-minute break. So let's come back at 1:35, and then we'll jump into it after having that break. We're going to be multiplying polynomials. It's going to be very familiar in some ways, but then I'm going to give you I'm going to break this down very explicitly, because there are certain problems when you're multiplying polynomials that are very apparent. They're very basic. You've done them before. We just weren't calling them multiplication by polynomials. And then there's some other cases where you have to be very mindful of what you're doing, what operation is being performed, and how that affects the exponent on the terms that we're multiplying. Okay. So let's jump into some problems. I'm going to break this down into sort of different categories that, it would be useful for you guys to be able to identify when you're working with one category versus another. Okay, so the first category is just multiplying a monomial by a polynomial. Okay, and I don't think I defined this word here before yet. So a monomial just means, you could imagine, one term. Everything else we'll just call a polynomial, right? We don't really have special names for anything beyond 3 terms. So one term polynomial is called a monomial. A 2-term polynomial is a binomial. 3 terms is a trinomial. And then after that, mathematicians get lazy and we just call everything polynomials. Okay. But even monomials, binomials, and trinomials, you could just call a polynomial. But it's just clearer when you say, okay, we have one term here. Okay, so one example of multiplying a monomial by a polynomial you've already seen. Let's do 5 times 3x to the 4th minus 8x squared plus 7. Okay. Can anybody explain how you would go about doing this, or maybe take a guess at how you would multiply this?
Distribute.
Yeah, so we learned it as distributive property, and that's all you're doing here. So what I want to do is like, okay, why is this multiplying a monomial by a polynomial? Well, we said before that this number can be thought of as a monomial, and it's being multiplied by this expression over here, which is a trinomial. So we have a monomial being multiplied by a different polynomial. But in any case, whatever you choose to call it, however you want to describe it, you're going to be doing the same process of just distributing the 5 or multiplying the 5 by each of these terms. So we should have 15x to the 4th minus 40x to the 2nd plus 35. And that will be the result or the product of that multiplication. Does anybody have any questions about that? Okay, well now we're gonna need to take some, have some mindful presence, take special care with this next one. 4x times 2x to the 7th plus 8x to the 3rd minus 9. And again, we're multiplying polynomials. So when you look at this, one way of imagining this problem is that this first thing is a monomial. It's a single polynomial term. And it's being multiplied by this polynomial in parentheses, which you could call a trinomial. So here, you're going to use the distributive property in the same way that we did in the problem above. But there is one difference. Can anybody guess what the difference is?
The x, you have to add the exponents, maybe?
Yeah, exactly. That's exactly right. So let's just take it one term at a time, right? We're still going to have to distribute this 4x times 2x to the 7th. Now that was similar to a problem that you guys saw last class and on the homework. And we said that when you multiply this, that you can multiply the terms or the factors in any order, that you could do 4 times 2, and that would give you an 8. But then x times x to the 7th power, that we have the same base, but with different exponents. And that's why we learned the product rule that says you have to add those exponents. Because if we wanted to break it down further, we could have x here times x, 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 right? You would have a total of 8 x's, which is why when you multiply these two terms, you should get 8x to the 8th power. Does that make sense? So that's the thing that you need to be very careful of, because now that we have the same base being multiplied by this term that also has the same variable base, you got to add those exponents. So what I would recommend is sort of doing this thing where, if it's helpful, cover up the terms you're not using, and then just focus on the terms that you're multiplying. So if I multiply 4x times 8x to the 3rd power, what should I get?
32x to the 4th.
Yeah, plus 32x to the 4th. Does anybody have any questions about that? And then again, just cover up the one you're not working with as best you can. And then what should 4x times negative 9 be?
Negative 36x.
Yeah. Does anybody have any questions about that multiplication? Or about why the exponents change? So last time when we went through all those like esoteric exponent rules, it was not just to make you do needless work. We were building up to this because you needed to know those exponent rules to see that they're going to come into play now that we're multiplying polynomials. So because we cannot combine like terms, this is going to be the end of the story. That is the result or the product of multiplying this monomial and that trinomial. Does anybody have any questions? Okay.
Just one, because
Yeah, go ahead.
because we have 4x, right? We cannot add or subtract the x, but we can multiply it when they have different exponents.
Oh yeah, definitely. It's a little bit strange. So what I'll tell you is that you sort of have to remember this, and it's sort of sort of, it's a little hand wavy. It's a little do as I say, not as I do. But you can multiply. Let me say, exponents may change upon multiplying or dividing variables. But that goes in line with what we learned last time, the product rule with exponents and the quotient rule. Yeah. I can never think of like a good explanation as to why this fact is true. I could come up with an example, but like the example wouldn't be very it wouldn't be it would not sort of connect to something that would feel familiar. So so I think that it's better to just say, okay, just remember that when we're adding and subtracting polynomials, the exponents don't change. When you are multiplying or dividing polynomials, the exponents may change. Right? We see that in this first example, when we multiplied a monomial by a trinomial, the exponents didn't change because when you multiply a plain number by things, you just multiply the coefficients. And there's not, this is like x to the 0 power. And if you were to add those exponents, 0 and 4 would remain 4, 0 and 2 would remain 2, 0 and 0 would remain 0, if that makes any sense. But yeah, you have to think about this as multiplying x times x to the 7th. How many x's do you have in total? Right? You can write that as an exponent expression, x to the 8th. X times x to the 3rd would be x times x times x times x, which is x to the 4th. Okay, so that was the first case, multiplying a monomial by a polynomial. Now, the second case, multiplying a binomial by a binomial, which is slowly building up. So that was 2, this is 3. We could do x plus 5 times x plus 3. Okay. So again, here I have 2 terms, so we can call this a binomial, x plus 5. And then over here we have a different polynomial expression, but it's also a binomial. And it's looking a little fuzzy. Let me see if I can. There we go. So can anybody venture a guess as to how I go about multiplying these?
X times x, and then 5 plus, and then 5 with the 3? Or do I have to do like what it calls that, like x times x and then x times 3, and then 5 times x and then 5 times 3?
Yes, that last thing that you just said is perfect.
Okay, it makes more sense. Okay.
Yeah. Okay. So the way I think about it, or the way my friend Pete, who's a coordinator of Math World, likes to describe this, is the handshake method. And I think that this analogy makes a lot of sense, or at least it makes intuitive sense to students. Imagine that you and a friend go to a party, and this party is sort of a lame party, and there are just 2 other people there. maybe it's a quiet get together, you know, not really a party. But in any case, you met online with this group of people, of like-minded individuals, and they're not weird or anything. So you decided to go over to their place, socially distanced, wearing a mask. Everybody's vaccinated. Let's go with that. But since you don't know them, you have to introduce yourself to both of them. And then your friend doesn't know them either. So your friend has to introduce themselves to this person and that person. Okay. So everybody, once this person has shaken their hands and we've gone ahead and done those handshakes, then everybody knows each other at that point. So that's how we're going to go about multiplying this. But this is just another way of saying distributive property. Or distribute. You will hear me just call it distributing. And that can be a little bit confusing for some people because mathematicians will say like, oh, just multiply. And when they say multiply, they might mean multiply in the traditional sense, or they might mean distribute, because they're both really the same thing. So what I do when I write this out is I'll draw arrows all over the place. Okay, so if I'm going to do the handshake method here, what I'll do is take the x and I'll draw an arrow here and here, and then run through that multiplication. So x times x, we're going to simplify that into an exponent expression. So x times x is going to be x squared. X times 3 is going to be plus 3x. And then we'll go ahead and take this guy over here and multiply here and here. So I always do the 2 arrows above, the 2 arrows on the bottom. Now that gets a little bit cumbersome when you have bigger polynomials, because then you'll have arrows going all over the place and you need to be careful with that. But in any case, 5 times x is going to be positive 5x. And then 5 times 3 is going to be 15. So we've expanded the polynomials by multiplying them out. And now to simplify this expression, you always want to simplify at the end. Do we have any like terms? Well, yeah, these two middle terms seem like they're like terms. And that tends to be the case. So we'll go ahead and combine our 3x and our 5x into 8x. So we have x squared plus 8x plus 15. And it turns out that when we multiply those two binomials together, that we get a trinomial. It's not always the case that you get a trinomial. It really depends on the variables that are in the original binomials. But a sort of interesting thing is that another way of looking at this is that you had a linear equation here, or a linear expression, multiplied by a linear expression. And then, does anybody know how to say the word squared in Spanish?
Cuadrado.
Yeah, squared in Spanish is it spelled like this? Cuadrado.
Correct.
Okay, it's not a Q, right?
No.
Okay, well, it turns out that if you have a linear equation times a linear equation, or a linear polynomial times a linear polynomial, that you end up getting a squared term here. And we would call this trinomial a quadratic trinomial. Okay. Now, the only reason why I'm throwing this additional vocabulary at you is because we're actually building towards solving quadratic equations at some point. We're still a little ways off, but it turns out that, you know, we had a whole unit on solving linear equations, and now we're gonna work towards slowly building up to solving quadratic equations. Okay. But we need more practice multiplying these binomials. So let me give you another example, and you guys can work it out. Let's do 5x to the second power minus 7 times negative 3x to the third power plus, let's do x. Okay, so take like 2 minutes to try to work this one out. Does anybody have any questions? Anybody just completely stuck? Does anybody have an answer for this one already?
I got negative 15x to the fifth power
Okay.
plus 5x to the third power
Uh-huh.
plus 21x to the fourth power
No.
to the third power
Yes.
minus 7x.
Yes. Okay. So we're going to take the first term, multiply it by each of these terms, right? So that's where we'll have to be careful and just, visually focus on the ones that you're working with. So what I do is, and this might seem silly, put your finger on the term that you're multiplying together so that you don't lose track. Like physically touch the page as you're doing this. Okay, so 5x squared times negative 3x to the third power. Start with the numbers. 5 times negative 3 is negative 15. X squared times x to the third power. You add those exponents, so x to the fifth. 5 times, there's an understood 1 here, so that's just going to be a 5. But x to the second times x to the 1 is x to the third. So we should have plus 5x to the third. Then we can move on to the next term and make sure that everybody shakes hands. So I'm going to draw my little arrows. Negative times a negative is going to be a positive, so I'm going to write a plus sign. 7 times 3 is 21. And then I don't have an x here, so I'm just going to say that this is x to the third power. Okay, you could think of it like there's x to the 0 power here because there's no x's. So 0 plus 3 would be still 3. Okay, negative 7 times x. Okay, that's just going to be negative 7x. You could think of it like x to the 0 power, x to the 1 power, so there's just 1x. And then always when you do that handshaking, you just want to make sure that that you go ahead and combine like terms to finally simplify the expression, right? Because I wouldn't go to the store and say, I need negative 15 apples, positive 5 bananas, positive 21 bananas. I would just say that these are both bananas, so let me just call it what it is. That's going to be 26, x to the third, or bananas. I should use like more exotic fruits, like durians and pomegranates and stuff like that, but I think that we'll just stick with apples, bananas, and oranges. Yeah, but this should be it. Does anybody have any questions? Is anybody completely lost on that process? Or does anybody have any comments on another way that you've learned to do it? There's multiple ways to go about that, this process, but I think that the handshaking method is probably the most versatile way to do this. And so I don't want to like get you guys bogged down with multiple methods. So let's move on to the next case of multiplication. Okay, so you might multiply polynomials, and you might multiply 3 polynomials at the same time. So you might have something that looks like this. 4x to the second power times x squared minus x plus 7 times x plus 2. Okay, and just to, break it down, what am I looking at here? It looks like a lot of, like just a alphabet soup, right? With numbers and letters all thrown together. But you really want to break down this problem into the larger or most important features. What we're looking at here is that we have a monomial times a trinomial times a binomial. Or in general, we're just multiplying 3 polynomials together. Okay. So does anybody know how we would go about slowly working this down so that we can multiply the terms together and simplify the expression? Anybody have any ideas?
Distribute
Yeah, what would I distribute though?
the 4x into the first trinomial.
Yeah, let's do that. So we're first going to sort of ignore this binomial here and just focus on the first 2 polynomials. So let's go ahead and distribute, and maybe I'll throw this here and draw these arrows. Go ahead and distribute that out. So we should get 4x to the 4th minus 4x to the 3rd plus 28x to the 2nd. You guys feel okay with that? Any questions there? Is that the same thing that you guys are getting?
Yes, just not as fast.
Yeah, and it'll take practice to pick up the speed, right? You're always going to have to, crawl before you walk and walk before you run. So if you try to speed it up at the very start, you're going to start making lots of mistakes, and then it's going to be harder to learn. So just be patient with yourself. Obviously, in class, I sort of have to run through at a certain pace. So that's why the video exists. Anyway, once you've multiplied those out, you'll go ahead and say like, okay, 1, 2, 3, I have a trinomial now. Let me throw that in parentheses because I still have some multiplying to do. Now I've taken care of these 2 things. These 2 polynomials became this new trinomial. But I need to bring this binomial down and multiply this out now. So can anybody tell me how I would go about multiplying these 2 polynomials out?
But you multiply the x through the 4x4 and the x for the minus 4x3.
Yeah, And then here too.
Uh-huh. And multiply the x for 28x.
Yeah, yeah. And then,
And then
you would take 2 and
Yeah.
then the same process.
Yeah, correct.
Okay. Now,
Eight.
some of you guys might be asking, okay, well, why did Yvonne start with this polynomial and multiply the x here, here, and here, and then the 2 here, here, and here? What if we multiplied this 4x to the 4th, this term, by these two, this one by these two, and then this one by these two? And the answer is, it doesn't matter. It really doesn't. You have to think about it like the handshaking method. If we're going to a party, me and a friend, and we meet 1, 2, 3 people that we've never met before, I will have to shake each of their hands, and my friend will have to shake each of their hands. And another way of saying that is that this stranger will have to shake both of our hands. This stranger will have to shake both of our hands, and this stranger will have to shake both their hands. So it doesn't matter which way you think about it. It's just sort of simpler to start with a smaller polynomial and then go 1, 2, 3, and then take this guy and go 1, 2, 3. But you'll end up with the same result. Okay. So let's do this, sort of multiplying in the leftward direction. We'll take x times here, here, and here. Just going to rain down hellfire and multiply these x's out. So we'll have what? 4x to the 5th minus 4x to the 4th plus 28x to the 3rd. Are you guys okay with that? And then we'll worry about this guy over here and multiply it here, here, and here. We're not really raining down hellfire anymore. This is more like what, like missiles in a submarine or something? I don't know. Landmines, maybe? In any case, we're just multiplying. I'm just getting off track. So we have positive 8x to the 4th. Go ahead and put your fingers if you get distracted or lost. Okay, so 2 times negative 4 is negative 8. So that's going to be negative 8x to the 3rd. 2 times 28 is going to be 56x to the 2nd. Ran out of space there a little bit. It's okay. Does anybody have any questions about that? And just count how many terms you have here. 1, 2, 3, 4, 5, 6. Notice that I had 2 terms here and 3 terms here. So it turns out that 2 terms times 3 terms ended up with 6 terms. Okay. So that's just like to keep sort of some accounting of how many terms you should end up with. But in any case, now we're just going to simplify by combining like terms. So we have x to the 5th. I'm going to put these in order of descending exponent. So this is my only x to the 5th. I'm going to put that one first. Okay, and maybe it's helpful to cross out the ones you've written down. We have x to the 4th here, negative 4 plus 8, and we're talking about apples here. So that will be a positive 4, positive 4x to the 4th. When I'm added these two together. Does anybody have any questions about that? Because I'm just going to cross them out once I'm done with that arithmetic. Then I'm looking at these 2 terms. Since it's x to the 3rd, we're talking about bananas. So 28 minus 8 means I'll have positive 20 bananas. And then this is the only x to the 2nd power. So I'll just bring that down. And I cannot combine like terms. So that has to be the end. Does anybody have any questions about that one? Now that one might seem a little intimidating because it's just a lot of keeping track of what you're multiplying. And then combining like terms, I always think of it like an accordion. You just go ahead and squeeze that accordion together, and then everything comes to the simplest terms. Once you can't combine like terms, don't try to keep going. Okay, just know that you cannot combine like terms. There's nothing similar here. X to the fifth, x to the fourth, x to the third, x to the second. You're done. Any questions? Comments, concern, confusion? Okay. Let me give you an example of multiplying 3 polynomials so that you can work on your own. Take about, I don't know, 3 to 5 minutes to do this one. What are we on? 6. Lots of multiplying. Let's go with 5x squared times x squared minus 49. And then x squared minus 9. Okay. Oh, there we go. So just take a moment to work through this one. Maybe 2 minutes, 3 minutes, whatever it takes.
Am I overthinking this? Do I need to do the handshake first?
With these guys,
Yeah,
you could. It won't make a difference.
okay.
You could think about it this way, like if you were just multiplying 3 numbers, let's say 5 times 49 times 9.
I could just start with distribute to everything.
Well, I mean, when you multiply 3 numbers together, you're really doing either these 2 things together, and then you get the result and multiply that by the remaining thing.
Okay,
But it doesn't matter what order. You can multiply 9 times 49 and then multiply the 5 later.
okay,
So in our last example, we said ignore this last polynomial and just distribute here first, get that result, and then multiply it by what's remaining. But if you prefer to multiply out the 2 polynomials first and then multiply the monomial later, the order is not going to matter, just like with multiplying numbers. Okay, does anybody have an answer for this? Or do you guys want me to just like run through it because well, you know, we're building up confidence too right now, right? So are you guys still working on it, or do you want me to jump in and sort of run through it?
Well,
I
I'm
have
done.
an answer.
Oh, yeah, what's your answer?
I got 5 x to the power of 2 minus 245 x to the power of 2 plus 5x squared minus 4x squared.
There's too many x squares here. I'm gonna hold this to the side for a second and let's sort of see how we can go about doing this. Now, when you multiplied some of these things out, I think that you might have forgotten to, let's see what you did. Let me see. I'm trying to like break down, basically read your mind. So 5 times 49 is how you got the 245. So it looks like you tried to multiply this one with this one first. So we could start there for sure. Take this guy, multiply it by both of these. But what you forgot to do, or maybe you just misspoke, I'm not sure. This should be 5x to the 4th power because x to the 2nd times x to the 2nd gives you x to the 4th. This one's good though. This should be 5 times negative 49 is negative 245 x to the 2nd power since we have an x here and we don't have an x here. So we'll bring that x squared down. At that point, we need to say, okay, this was the result of that first multiplication. Now we need to bring this guy down and multiply it again. So we'll use the handshake method to multiply this. We'll take this first term, multiply it here and here. So we should get 5x to the, now we have x to the 4th times x to the 2nd. So that'll be x to the 6th. And 5x to the 4th times negative 9 will be negative 36. And then there's no x's here, so this will just be x to the 4th because we're doing this multiplication here. And then finally, we'll take this thick boy right there, multiply it by these over here, and we get negative 245 x to the x squared, that'll be x to the 4th because you add the exponents.
I think you messed up on your math.
Oh, did I?
Isn't it
minus
5 times 9? It's 45.
Oh, did I yeah, I totally did.
It's negative 45x
This
to the
one
4th.
and here. This, wait, where? This and this and that is 45.
Yeah.
Good catch. Keeping everybody on their toes. 45. I'm going to give away my political affiliation right now. This number I would just hope to forget, just hope that it never happens. I've just totally scratched it from my number line. Anyway, anyway, thanks for catching that. I make mistakes like you guys sometimes, so don't be too hard on yourself when you make mistakes. Be the appropriate level of hard on yourself, okay? In any case, we have blah, 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 blah. That should be that. Good. This and this and that. Okay. That's great. And then this times 9 will be a positive since it's a negative and a negative. And nobody has time to multiply these big numbers. So 245 minus 9, not minus 9. Oh, God. Need more coffee. Times negative 9. Oh my God. Is that what you guys got? 2205?
Yes.
Lord. Anyway, that's what we're going with. 2205 x to the 2nd power. And let me just double check this. X to the 6th, x to the 4th, x to the 4th, x to the 2nd. Okay, so now we're just going to combine our like terms. These guys in the middle tend to be like terms. So we'll have 5x to the 6th. 45 and 245 will be 290. So this is going to be negative 290 x to the 4th plus 2205 5x to the second. Boom. Is this what you guys got, or am I making a fool of myself?
No, that's what I got.
That's what I
Okay.
got.
Okay.
Thank you. Awesome. Does anybody have any questions about that? I know that I really hate making mistakes in the middle of lecture because I think that I lose some people. And I just want to make sure that everybody's on track. Did I lose anybody? All right. Okay, what is the next example we have to do? Multiplying two trinomials. Well, I think that we're getting pretty adept at using the handshake method. And if you rely on the handshake method, then you should be good. So the last thing that we need to cover before we let you go is what are we on? Case C. This is case D. And it's raising a polynomial to a power. Okay, now the most common thing that you'll see is something like this. We would call this a perfect square trinomial, or a perfect square. We just call it a perfect square maybe, but we would have x plus 2, something like that. And then this polynomial would be raised to the power of 2. Can anybody venture a guess on how you would go about simplifying this expression?
Would you put x plus 2 in parentheses and then x plus 2 in parentheses next to it?
Exactly. That is exactly what you'll do every time. Remember the definition, right? Definition of exponents. So x to the second power is x times x. That means that if you have x plus something to the second power, then you're going to have 2 copies of that polynomial. And then you'll multiply it out. Okay. Now, the reason why I put this little definition here to remind you is that because, well, I'll talk about it in a second. Let's just go ahead and do that handshake method to go ahead and simplify this. We should get x squared plus 4x plus 4. Is anybody confused as to how I got this?
Could you put another step in there,
Yeah,
then
you
combine 2x to
Yeah,
make it 4?
you definitely could. And I expect you guys to do that, because the more of these polynomial operations you do in your head, the harder it's going to be to like keep track of what you're doing. So write down each step. Now, for me, I'm very familiar with this kind of a polynomial, and I know that there's this formula that if I have x plus a squared, really that's the same thing as x squared plus 2xa plus a squared. But so what this formula here is saying is that if I have this polynomial, that what my answer will end up being is x squared, the first thing squared, and then it'll be x times 2 times the exponent. So 2 times x times a, so 2 times x is going to be 2x times 2 is going to be 4x. And then a squared is just 2 squared. Now that's if you get comfortable with that formula. You don't have to. I highly recommend not even worrying about that formula and just doing the handshake method every time.
Okay.
But you know, one of the things when math starts to get more complicated, it's sort of useful to know these shortcuts so that you cut down on time. But if you can work the handshake method and get fast at that, that'll be the same, right? And maybe you'll make fewer mistakes. Like I said, the less you do in your head, the fewer mistakes that you will make. Okay. So raising a polynomial to a power. So let me give you this one. You guys work on x to the second minus 9 squared. What should this be? Does anybody want to walk me through this one?
Yeah, I did my parentheses, x squared minus 9 parentheses, and then parentheses, x squared minus 9 parentheses.
Okay. And then what'd you do?
And then I did the handshake on that. So I got x to the 4th power
Cool.
minus 9x to the squared
Mhm.
minus 9x squared plus 18. And then I combined my like terms. So I
Be
got,
careful there. Be careful.
okay,
You did negative and negative to give you a positive. That was great. But then you added these numbers. It should be 81 because we're multiplying.
oh, okay.
Yeah.
So then it came out x to the 4th power minus 18x to the
Second.
2nd power plus 81.
Yeah. Perfect. Yeah. So when you're doing this, that's a common, autopilot mistake that people will make, including myself, where you'll look at the numbers, you'll know sort of that you're multiplying, but then in your head, you'll accidentally like add them. So just be careful with that. So I want to look at this one again because I think it's instructive to look at this problem and to anticipate the errors that you guys are going to make in your heads when you're like strapped for time or particularly nervous. So let's do this one again. A lot of times, a common mistake that students make is that they'll say, okay, x squared minus 9, for instance, squared. And you'll be, frantically trying to finish the test or finish a quiz or try to do the homework as fast as you can because maybe you have to go to a doctor's appointment or something. Whatever it is, whenever we're like our minds are racing, we're gonna lose focus, lose track of what we're doing. And a lot of times students will say like, oh, I remember vaguely that when there's an exponent here, that can't I do just multiply this and this? And then say, okay, well, the product rule told me that I should be able to write this as x to the 4th minus, let's call that 81 because 9 squared is 81. Don't do this. Resist the temptation. And when you write this in your notes, I want you to write this big X and I want you to write resist the temptation with 3 exclamation points because it's super important that you not make this very, very, very common mistake. Now, the reason why this mistake exists, I think, is because if you recall, we had the product rule for exponents last time. That said, if we had a times b inside parentheses and that was raised to a power, that you could take that power and sort of distribute it. and then write this as a to the nth power, b to the nth power. That's perfectly okay. Because we're multiplying inside the parentheses. But when you have x plus something raised to the second power, for instance, that you have to write, you cannot write x squared plus a squared. That's not going to be correct. Okay, so don't do that. Similarly, if you have x minus a number squared, the temptation is to say that this is x squared minus a squared. And that would not be correct either. You have to fall back on the definition for this exponent. So always write copies of the polynomial. Don't try to use this shortcut, because this shortcut is not a shortcut, it's just wrong. Right, because we looked at this problem already, x squared minus 9, and if you squared it, you did have an x to the fourth, and you did have a positive 81. But if you did that shortcut thinking that you're going to save some time, you're missing this middle term. So that's just something to be aware of. Be very careful when you're raising something to a power. So I want to give you one example, and I think we'll call it a day. What are we on? Number 9. Let's do x minus 1 to the third power. Take about 3 to 5 minutes to work on that one. And my note is to always write, and I'm going to put n copies of the polynomial, where n is just going to be whatever that exponent is. So when you start this problem off, it's really x minus 1 times x minus 1 times x minus 1, in the same way that 2 to the third power is 2 times 2 times 2, or 45 to the third power is 45 times 45 times 45. Okay, how are we doing here? Is that what you guys got?
Yes.
Cool. So I skipped some steps here, but that's just because I wanted to compare results to results. If you didn't get this, then either you're off or I'm off, and chances are that it's you. Although sometimes it is me, so don't worry about it if I did get it wrong. You know, I don't judge you harshly for making mistakes, and I would hope you afford me the same courtesy. You know, when I started off this problem, I said, okay, let's multiply these two polynomials together. These two polynomials then turned into this trinomial. You might have had an intermediate step here, and then you would have combined like terms and gotten this trinomial here. At which point I said, okay, let's just use the handshake method to multiply this guy here, here, and here. And what I did was I wrote it down on one line. And then when I multiplied the second term, which is this one over here, not the x again, there, and there, this -1 times each of these produced some term that I put on the second line, but I just lined up my like terms so that it would be easier to sort of tabulate or combine them. Right, so now I have a column that has my x to the third powers, my column that has my x to the second powers, and my column for my x's, and then my column for my just plain numbers and my constants. And then I just added straight down. So x to the third comes down, this is -3. That's going to be +3, and then that's going to be -1, and then we just have the appropriate variables on them. That makes sense? Yeah, and when I ask, does it make sense? I just mean, yeah, broadly, does it seem to make sense? Not like, are you fast enough to keep up? I know that sometimes I go fast, but you know, there's a certain pacing that we have to do to get through the lecture. So if you are having trouble with these, well, you're gonna have plenty of time to go into the homework and practice some more of these. So I'm gonna open that up here in a second. It's gonna be, I think this one is homework R. Ooh, that's an R, that's not a B. R.3 in MyLabs Plus. So we have that to look forward to. And then I'm also going to go ahead and try to make a discussion in Canvas that I want you guys to respond to. That's going to get us ready for next class, which is going to be factoring polynomials. Okay, now you might notice that today we did addition and subtraction of polynomials. We did a lot of that. We did a lot of multiplication of polynomials, but we didn't do division. Well, when it comes to polynomials, factoring is going to be similar to division. Okay, it's not exactly the same, but that's what we're going to get into next time. And there's actually 3 different factoring techniques that we're going to teach you. So it'll be important for you to go into MyLabs Plus and get up to speed with the homework so that you're ready to receive this new, and at some point it's going to be a little bit crazy, material that we're going to get into next time.
So what we did last week and today, that's the homework we're going to work on.
Yeah.
Okay.
Yeah. So my thinking here is that we should be wrapping up the review and the test, because the new material, the stuff on the exponents, this stuff on the polynomials is building up to the next test. But these are the simple building blocks that are going to get us towards some more complicated stuff. Okay.
And this homework's due Wednesday?
The homework that I'm going to open up now is going to be due on Sunday. And
Okay.
I'll probably push both of those homeworks, the exponent one and this one, to Sunday. But as always, if you guys have further questions, you're welcome to hang back. But this is the point of the lecture where I let you guys go. So if you don't have any questions, have a nice rest of your day.